and other one is indirect approach, right? As I told about indirect approach, right, I'll be dealing it during offline sessions, right? And direct approach, right, in regular sessions I'll be taking. So in last class, it was a short session. It was only for 40 minutes, right? We have discussed about one quite straightforward method for obtaining FM demodulation, right? So there, what if you remember there, what we did is we pass the FM signal S of t through a differentiator, right? And after that, what the differentiator does is whatever information was residing inside the frequency variation, right, after it is passed through a differentiator, right, it also brought in some variation in amplitude. So we got a sort of hybrid signal, right? Hybrid signal in the sense it has actually what amplitude variation as well as frequency variation, right? So if you remember FM, right, it is supposed to have a constant amplitude, right, and the information is stored within the zero crossings or variation in frequency, right? But after we passed it through a differentiator, what happened is we had an like envelope which is varying, right? So we have seen that in last class, right? And after we pass that differentiated signal through an envelope detector, we were able to get back the message signal. Then I told further, right, the obtained demodulated signal, it will have some DC bias, right? And so in order to overcome that, we'll have to do some signal conditioning. Those are some of the basic things I've told, right? So in today's session, we are going to study about the direct method, which is called actually what? Frequency discriminator method. So I would like to start with the submission, like the same method, same frequency discriminator method, or balanced frequency discriminator, or ideal frequency discriminator, right? In different textbooks, they are presented it in different ways, right? And so the approach which I am going to discuss here, it is according to the prescribed textbook, that is our Simon Hakin textbook, right? But if you want a slightly simplified approach, you can even refer the local or the materials which is available, right? I don't have any issue, right? But I think we should stick here with the prescribed textbook, right? So with that note, we'll start with our session, right? So before I move ahead, so I would say it's not an easy thing to digest whatever I'm going to tell. I would like to start with a right warning, right? It's not that straightforward, right? We will be using many aspects or concepts which you are supposed to know, or which you might have learned, right, in smaller classes, and some of the techniques which you have not yet learned, right? So like the concept of complex envelope and all. So whatever is required, I will discuss here. So I request you to maybe along with me, you can take down whatever is being discussed here, right? So the topic is FM demodulation, right, using frequency discriminator, and it is a direct method, right? So FM demodulation using frequency discriminator using direct method. So if you take your prescribed textbook and start reading, I'm sure you're going to get confused, right? So for that, maybe I'll try and help you out, right, how to tackle such, right, topics, right, which looks complicated in the first sight, right? You feel it, you can't digest it. So how to tackle that? We'll see, right? So we'll go step by step, right? This frequency demodulation, right? So what do you mean by frequency demodulation, right? Frequency demodulation, right? So these ideas you should have, right? It's recovering message, right? Frequency demodulation means it's recovering M of t from S of t, right? So from the modulated signal, we have to recover the message signal. That is actually what frequency modulation. It is exactly opposite to that of modulation, right? What is modulation? From M of t and C of t, we will get S of t, right? So in demodulation from S of t, we are supposed to get back M of t, right? So I hope that that part is clear, right? So this demodulation is actually, especially the direct method of demodulation, right? it actually the objective of this, right? Maybe I can write objective of this direct demodulation, right? Is to please take it down along with me, right? Is to produce a transfer characteristic that is inverse of that of modulator, right? So what FM does is FM like produces S of t from M of t, right? So here in demodulation, what we need is from S of t, we need to get back M of t, right? Or in other word, right? So what actually was FM direct FM modulation? What it does is this instantaneous frequency Fi of t was varied in FM. That's what I'm telling. In FM, what was happening? Just keep in mind, instantaneous frequency Fi of t was varied according to instantaneous amplitude of M of t. Right. Here, frequency was varied according to M of t. Right. In FM modulation. So in demodulation, the reverse should happen. The reverse in the sense that is amplitude should vary according to Fi of t, right? So this is what is meant, right? Inverse to produce a transfer function or transfer characteristics that is inverse of that of frequency modulation. When they said that in textbook, they mean, right, amplitude of the system, whatever demodulator system, right? It should vary according to instantaneous frequency. That is meant by like producing a transfer characteristics that is inverse of that of FM, right? So till now, is there any doubt, right? So please do let me know, right? I'm telling it's not that actually what easy or straightforward. It has some complication within it. I'm starting with that submission, right? So please do follow whatever is being discussed here and try to take down lecture notes, right? So far, is it clear what a direct demodulator is supposed to do? So we have S of t. It has information residing within the variation in frequency or in instantaneous frequency, right? That instantaneous frequency, right, has to be actually what converted to amplitude variation. So basically, it's something similar to what we have done in last class, right? It's not something similar. It's you may even be able to appreciate it is exactly the same thing what we have learned, but now we are going to see the mathematics in detail of that, right? So so far, is there any doubt? Please type in yes or no. Right. I want to make sure two things. You people are taking it down along with me. Right. Right. So okay, I'm telling very simple things. Right. So far, I've told only very simple things. Right. So so far it's clear. Right. Now, uh, what is our S of t FM signal, right? So we'll assume our FM signal, right? FM signal, we'll represent it as S of t, right? And let the carrier frequency be FC and the bandwidth be BT, right? So this is carrier frequency, right? Carrier frequency is FC and bandwidth is BT. So this is we are assuming we have an FM signal whose time domain expression will be represented as S of t, right? Its carrier frequency is FC and bandwidth is BT, right? So what does that mean, right? It means, right, in if you see frequency domain, if you see frequency domain, if this is actually what FC, right? If this is FC and minus FC, right? The signal will have components, right? So this is actually what arbitrary shape, right? I'm not right. So in fact, it should be what discrete, but I'm just to show. See, this is S of F, right? Same mode of S of F, right? So when I say the center frequency or carrier frequency is FC and bandwidth is BT, right? What you should appreciate or what you should what should come to your mind is, right, the uh, signal will have frequency components, right, centered around plus FC and minus FC, and it will have components from FC plus BT by 2 to FC minus BT by 2, so that, right, total bandwidth, right, this is the total bandwidth, right, this is the total bandwidth, right. So it's not that FM signal won't have bandwidth above actually what FC plus BT by 2 or below FC minus BT by 2. Like someone has typed something, like okay, someone is trying to join. Yeah, okay. So while I'm explaining this, if you have any doubt at any given point, please feel free to stop me and clear your doubt. Just try once. Anyhow, for attendance sake, at least you're sitting in class, right? Try to what, learn something, right? So it won't be a waste of time, right? So okay, so we are assuming this. It's an assumption, right? In practice, actually, what we know, a FM signal will have frequency, right? Spanning from plus infinity, spanning to plus infinity, right? But we have seen some of the conditions or some of the like empirical rules using which we can identify the significant range of bandwidth of FM signal. So there is something called Carson's rule, and we have universal uh, graph of uh, bandwidth, all those things, right? So using that we can find, but in our assumption, right, this S of t will have frequency content from FC minus BT by 2, FC plus BT by 2. You may be thinking, what is this BT? This BT is nothing but what, bandwidth of FM signal, right? It can be given by Carson's rule or whatever, right? So we are assuming with this. So now, can anyone tell me what is the time domain expression for this S of t? If carrier frequency is FC, carrier amplitude is AC, it will be AC cos 2 pi FCT plus 2 pi KF times. And if you are assuming the message signal is M of t, right, 2 pi KF times. Can anyone complete this? Right. Can anyone complete this? 2 pi KF times what is, right? Can anyone complete that time domain expression? S of t. FM modulated signals time domain expression, right? So remaining part has M of t and all. So what is that remaining part? That is my question. Integral M of tau d tau. Yes, exactly, Samar. Thank you. Right. So it is integral 0 to t M of tau d tau. Right. So this is our S of t. Right. This is our S of t. So this is what we have to start with. This is what we have. Right. So S of t has this time domain form, and it will have frequency contents from FC minus BT by 2 to FC plus BT by 2. So this is our initial assumption, right? So now we'll see what exactly is direct method. So in a nutshell, right, the very simple thing is actually what initially what we'll do is FM will take, right? FM will be converted to what, a hybrid sort of signal, right? Hybrid signal. When I say hybrid, right, it will have, it is actually what, it will have AM plus FM. AM plus FM in the sense this frequency also will contain the message, and it will have an envelope also, right? So an FM, right, as the envelope is constant, we are doing some operation, right? Some operation, it can be what, d by dt, or passing it through a slope circuit or discriminator or whatever. There are different techniques, right? So by means of some technique, we are converting this FM into a hybrid signal, right? So that hybrid signal will have information within its amplitude variation as well as in frequency variation, right? So but now if information is residing within the amplitude variation, we can always use an envelope detector, right? Envelope detector, right, to demodulate it, right? So but when we are using envelope detector, this amplitude modulation part or envelope of this message signal should satisfy some condition. We have seen what is that condition. In last class, we have seen what is that condition, right? So this is the basic idea, right? FM, it will be converted to some hybrid signal so that there will be amplitude variation also. Corresponding to the frequency variation, we'll introduce some amplitude variation also. Then that amplitude variation will detect using envelope detector, right? So this envelope, so that is what we are doing. So one typical example what we have seen is using a differentiator, right? So now when you say discriminator, frequency discriminator, right, you can maybe at the end, if you are able to appreciate that is equal to differentiator itself, right, I would be happy, right? So I think you have taken down all these things, right? I'll ask you at that time, you have to tell me, give me these results, right? Now we'll start with, say, direct method, right? Direct method. Direct method of FM demodulation, right? So in a direct method of FM demodulation, we should produce a transfer function or transfer characteristics that is inverse of that of FM, right? So in FM, what happens is, we have seen instantaneous frequency is varied according to the amplitude, right? So in direct method of demodulation, I'll write what should happen is instantaneous amplitude of the system should be varied according to the instantaneous frequency, right? So you are in fact going to design some system, you don't know what is the system, right? What should happen is, if you give some signal s of t here, according to change in frequency of this s of t, there should be actually what, change in amplitude, right? Output should reflect the change in frequency at the input as change in amplitude. So how can we come up with such a system, right? So knowing the spectrum of s of t is like this, it has frequency content from fc minus vt by 2 to fc plus vt by 2. Only these range of frequencies we have, right? Suppose we can come up with some LTI system, some system, right, which will give different gains or different levels of magnification to different frequency contents, right? So then it will serve a purpose, right? So that's what we are going to do. So our objective is to bring in instantaneous amplitude variation corresponding to instantaneous frequency, and for that, right, for that we can use a component called frequency discriminator, right? A component which can bring in or realize this um, objective. That's actually what frequency discriminator, right? It's called frequency discriminator, right? Frequency discriminator can bring in instantaneous amplitude variation according to, right? So this can be a frequency discriminator, right? So frequency discriminator. So basically, a frequency discriminator, what happens is, instantaneous amplitude, I'll write it as a subscript instantaneous, right? It will be proportional to instantaneous frequency, right? It will be proportional to instantaneous frequency. This is what a frequency discriminator does, right? So basically, a frequency discriminator, right, it consists of a slope circuit. I'll come to it. What exactly is this, right? A slope circuit followed by an envelope detector. Right. So basically, a frequency discriminator consists of a slope circuit and an envelope detector. Right. So this slope circuit, what do you mean by slope? Right. What do you mean by slope of a function or a graph or whatever? Slope is nothing but what? If this is y and this is x, slope is nothing but dy by dx. If this was t, slope would have been dy by dt. Right. So slope, right, let's go something to do with actually what differentiation. So now we'll see what exactly is actually what transfer characteristics of the slope circuit. So if we say the slope circuit has a transfer characteristics of H1 of F, right? The slope circuit has a transfer characteristics of H1 of F. So what actually is transfer characteristics, right? Normally, right? So those who don't remember what is transfer characteristic, normally an LTI system, right? LTI system will be represented using its impulse response, right? So if you give X of t at the input and if the output is Y of t, right? So then input and output are related as y of t is equal to x of t convolved with h of t, right? This is in time domain, right? So if you are taking frequency response of this, right? So normally the transfer function, right? Maybe if you take the Laplace transform or Fourier transform of h of t, right? H of s or h of f, that is actually what transfer function, right? So if you transform this into frequency domain, you will get y of f is equal to x of f into h of f. So transfer function is nothing but what? In this case, it is Fourier transform of our impulse response h of t, right? That is a transfer function. So now I'm calling the transfer function of the slope circuit as h1 of f, right? So this transfer function, right, it should satisfy two conditions, right? So I'll write here, right? This transfer function of the slope circuit should satisfy two conditions. It should be purely imaginary. And right, this transfer function should vary linearly with frequency inside a prescribed interval, right? Should vary linearly with frequency inside a prescribed interval, right? So these two conditions should be met. An ideal slope circuit, right? An ideal slope circuit should have a purely imaginary transfer function. Purely imaginary means it will have only what? Imaginary term j followed by, right, the transfer function, right, or magnitude of the transfer function, right? That will be, that is meant by purely imaginary. And this transfer function should vary linearly with frequency inside a prescribed interval. So what do you mean by a linear relationship between x and y, right? When I say linear relationship between x and y, right, so it should be like this: y should be equal to mx plus c, right? It should, right, the relationship, if we can actually what, uh, join the locus of all points, right? When it's moving in such a way that y is equal to mx plus c, you'll get a straight line with slope equal to m is the slope and c is actually what? Y-intercept. Y-intercept means actually where this straight line intercepts the y-axis, or when x is equal to 0, what is the value of y? That is actually what y-intercept. This is actually what linear relation, right? So if c is equal to 0, it means it's passing through origin, right? And slope is nothing but what? Dy by dx. Slope is nothing but dy by dx, right? So this is meant by vary linearly with frequency, right? So this transfer function, so if you plot a transfer function, right, if you plot a transfer function and f, right, it should be a function like this, right? It should be varying linearly with frequency. That is what is meant by this, right? So I hope this is clear now, right? But when one more thing what we have here is a prescribed interval, right? So which frequency interval are we interested in, right? If you remember, if you see this, I plotted the spectrum of our FM signal, right? Here the frequency spans from say fc minus bt by 2 to fc plus bt by 2, and also in the negative side, right? So what we need to do is we have all these range of frequencies, right? So if you see here, we have all these range of frequencies. So a slope circuit, right, should provide different gain for different frequencies. So maybe I can, right, realize it's something like this, right? A slope circuit, right? If it is something like this, right, you can see as frequency changes, it's linearly changing, and it is prescribed only with, sorry, within a frequency range. And similarly here also I can have some slope circuit like this, right? It's actually what this part within this frequency range, say fc minus bt by 2 to fc plus bt by 2, it's a it's a linear relation, right? It's a linear relationship. It's actually what something like mf, right? It's like mf, or it's minus mf. So this is one way. What is the meaning of this? That if you consider this particular frequency fc minus bt by 2, it provides a gain of 0, right? So hardly the frequency content fc minus bt by 2 can pass through this frequency discriminator, right? But as you keep on increasing the frequency, you can see it will be experiencing more and more gain, and it will provide maximum gain for fc plus bt by 2, right? And beyond this frequency range, it will be completely, right, attenuated or eliminated, right? So now suppose uh, all the initially in the input signal, right, all the frequency contents have same magnitude, right? Initially in the input signal, if all the frequency content have same magnitude, but when you're multiplying in frequency domain, what happens is you're multiplying this with this, right? So what happens, the resultant gain will be a function of this, will be determined by this, right? So that is the idea. So now we'll see what is that. So slope circuit, right? We'll see what is a slope circuit now, right? So this slope circuit, it should have a purely imaginary transfer function, and its transfer function should vary linearly with frequency inside a prescribed interval. So that prescribed interval we have seen, right? It should be from fc minus bt by 2 to fc plus bt by 2, right? This is a prescribed interval, right? So why? Because we have defined bt, right, and fc. That's why we are writing it like this, right? So now some prerequisite, right? Say maybe some prerequisite we'll mention now, right? Suppose I have a function like this, right? Suppose maybe I'll use, okay, suppose I have a function like this. Suppose I have a function like this. This is equal to what? This 2 pi a times f, right? So slope was 2 pi a, right? The slope was equal. This is frequency, right? And say this is, say, x of f. I'll write simply, right? This is x of f, right? So it is spanning from, say, 0 to bt, right? This is a function in frequency domain, right? So the slope is equal to what? So you can compare it with actually what the equation of a straight line, right? So you'll get to know slope m is equal to 2 pi a, and y-intercept c is equal to 0. We get, right? Now this is x of f. So now my question is, what will be x of f plus bt by 2, right? It is actually what? Shift, right? Maybe you have studied time shifting, right, of a signal, right? Similarly, if it is x of f plus bt by 2, my question is whether it will move right. When I say right, it's actually what? This direction, or it will move left, right? Left. This is right, this is left. So you can type in your answer, right? So if when you are doing plus bt by 2, it will move by an amount bt by 2, that is for sure, right? But my question is whether it will move right or left. You can type it in chat window. Sure. Why people are writing left? Shreyas and Tejasri has written it will move left. Right. Only two answers. I need some more answers. Right. Okay. At the end, right. I'll ask you to what um, upload it, or I'll ask you to switch on your video and show what you have written. I may call anyone randomly and I may ask you to do that. So please do take it down along with me. Right. Okay, fine. So the answer is left, right? It's correct. The answer is left, right? So it will be shifted left. So I'll draw it here. So when it is shifted left in the sense, right? I'll take this. I'm drawing here only. So it will be shifted left by an amount, right? So it will be spanning from bt by 2 to minus bt by 2, right? So this will be the new signal. So this is actually what x of f plus bt by 2, right? Now if I'm replacing this f with f minus fc, right? Now if I'm replacing this f with x, so I'm writing this is actually what y of f, right? Y of f is equal to x of f plus bt by 2, right? X of f plus bt, this is actually what y of f, whatever I have drawn with green color, right? Is that clear? It will be shifted left, right? Why? Because x of f plus bt by 2, right? So whatever should happen at that argument equal to 0 will happen at f plus bt by 2 equal to 0, or it will happen at minus bt by 2, right? So that's how you have to find. So we have already discussed it, right? So now this y of f is x of f plus bt by 2. Now my question is, what will be y of f minus fc, right? So this y of, I'll draw the new y of f here, right? I'll draw the new y of f here, right? The new y of f is like this, right? So the slope is 2 pi a. It spans from bt by 2 to minus bt by 2, and this is 0, right? This is our y of f, right? This y of f is obtained by shifting sorry, x of f by an amount bt by 2 to left, right? So now this y of f, if this is y of f, what will be y of f minus fc? So what will happen? As it is f minus fc, this entire thing will be shifted right by an amount fc, right? So shifted right by an amount fc. So if this is fc, right? If this is fc, this will be our say slope is 2 pi a. It will span from fc plus bt by 2 to fc minus bt by 2, right? Fc plus bt by 2 to fc minus bt by 2, right? And this is y of f minus fc. So is it clear how we got y of f minus fc? Y of f minus fc, if I'm writing it in terms of actually what x of f, right? I can write it as x of, so I should replace f with f minus fc. When I'm telling f minus fc, y of f minus fc, I should replace this f with f minus fc. That's what I'm supposed to do, right? So I'll get x of f minus fc plus bt by 2, right? So x of f minus fc plus bt by 2. So this is actually what x of f minus fc plus bt by 2, right? So now I need, right? So this was initially 2 pi af, right? This was initially 2 pi af, right? So now y of f, so we will write, right? So initially x of f was 2 pi a f. So now when I am replacing x of f with x of f plus bt by 2, right? If I am replacing f with f plus bt by 2, what I should do? I should replace here also 2 pi a f plus bt by 2. Now what will happen? This is shifted left, right? Now here if I am replacing f with f minus fc, right? X of f minus fc plus bt by 2. What I have done here, I have replaced f with f minus fc, right? Then here again I should replace f with f minus, so that is 2 pi a f minus fc plus bt by 2, right? So I will get, so this I can represent like this, 2 pi a into f minus fc plus bt by 2, right? Now right, so whatever we have discussed now, how many of you understood this concept? It's very simple thing, right? This you were supposed to what learn this in previous semester, right? So maybe you might have forgotten, right? Even if you have learned, right? So at times you might have learned the procedure in slightly different way, right? But did you understand like how 2 pi af, the difference between 2 pi af, 2 pi af plus bt by 2, 2 pi a f minus fc plus bt by 2? Are you able to what appreciate the difference between these three signals? Please, yeah, okay. So then, right, so the first right tedious part is done, right? So if you are able to appreciate this, then we can straight away write what is the, so we have right, so in direct method, once again I'll write direct method. What we have is we have a slope circuit followed by an envelope detector, right? Envelope detector, right? The slope circuit as a transfer function h1 of f, right? I'm telling the slope circuit as a transfer function h1 of f, right? We have seen the two conditions of an ideal transfer characteristics of slope function should satisfy, right? It should be imaginary. So imaginary means I should start it with actually what, a j, right? And the it should be defined over a prescribed frequency interval. So the this prescribed frequency interval which we are going to define it as actually what, from say sorry it is fc minus bt by 2 less than or equal to f less than or equal to fc plus bt by 2. And similarly on the negative side also, right? Similarly on the negative side it should be say minus fc minus bt by 2 less than or equal to f less than or equal to minus fc plus bt by 2. These are the prescribed frequencies. Why? Because our fm signal has significant frequency component within this range, right? And elsewhere it should be 0, right? And it should be elsewhere, right? Elsewhere it should be equal to 0, right? So from fc minus bt by 2 to fc plus bt by 2, right? It should be a linear function of frequency. It should be a linear function of frequency. So I'm writing it like this, right? J times 2 pi a. So why this j? It has to be imaginary. So j times 2 pi a, right? Then f minus fc plus bt by 2. F minus fc plus bt by 2. And for negative frequencies, it should be j 2 pi a. It is f plus fc minus bt by 2, right? So I just ask you to what, just like how we have done this, we have taken initially 2 pi af, then we have taken 2 pi af minus bt by 2 plus bt by 2, right? Then we have taken then we have replaced it with f, replace that f with f minus fc, right? I request you to what, try out this as well, right? So what will happen to that? So it's imaginary, and you can see it's a linear function of frequency. This fc and bt by 2, all those things are constants. Fc is a carrier frequency, bt is a bandwidth, right? So all those things are constant, right? So now we can, so what we can do is we can just try and plot this. We can just try and plot this, right? It's quite straightforward, right? To plot this, we have, right, this is, say this is plus fc and this is minus fc, right? So it should be a straight line from fc minus bt by 2. So I'll draw, this is fc minus bt by 2, this is fc plus bt, fc minus bt by 2 and fc plus bt by 2, and right, so the transfer characteristics should be like this, and elsewhere it should be equal to 0. So maybe I'll do it with, right, elsewhere it is equal to 0, right, and this, during this it should be equal to, the slope is equal to 2 pi a, slope is equal to 2 pi a, slope is equal to 2 pi a, right, this is slope, right, and similarly in the negative side, right, the negative side we can plot it like this, right, here slope will be equal to minus 2 pi a, it's minus fc plus bt by 2 and fc minus fc minus bt by 2, and slope is minus 2 pi, slope again is 2 pi a here, right, here slope again is 2 pi a, right, it's not minus 2 pi a, slope again is 2 pi a, here slope again is 2 pi a, right. So yeah, so this is what we have, this is h1 of f, right. So when, if you are trying to read it on your own, right, so in textbook they have initially given it like this, right, so it should be complex, it should be real, purely imaginary, and right, it should be linear function of frequency, then they have straight away given this, right. Now my question is, would you have understood that, right, whether whatever we have discussed so far, was that relevant, right? Now are you able to visualize the transfer function of this frequency slope circuit, right? Are you able to visualize it? If instead of discussing these things, if I was writing this thing directly, would you have been able to appreciate? That's my question. But now, are you able to visualize the transfer function of slope circuit? Right, you can type yes or no, not a problem. Right, if you are able to, you can write yes. Right, maybe at least forget about the negative part. The positive frequency part, are you able to appreciate? What is that? Are you able to see? It's a straight line with slope equal to 2 pi a, and right, it's shifted by an amount, say fc minus bt by 2 or fc plus bt by 2 towards right. Are you able to visualize that? Right. So this is our h1 of f. I'm not getting any response. Right. Please. Okay. Right. Yeah. Fine. So now what we'll do is, so this is our slope circuit, right? h1 of f. Right. h1 of f. And in fact, I should have written it actually h1 of f by j. Right. h1 of f by j. Why? Because it's purely imaginary. Right. There is a j here. Right. So I should have written it h1 of f by j. Right. And it's like this. Slope is equal to 2 pi. It spans from spans to these regions, and right. So, and what happens is, why this part is negative? Why? Because for negative frequencies, f will be negative, right? This f will be negative. That's why this part is negative. Even though slope is same, right? Even though slope is same, as for negative frequency, f is negative. This part is negative. This part is positive. That is the difference. So now what we are going to do is, right? So we have this s of t, right? S of t will be passed through a slope circuit, right? And it has a transfer function equal to h1 of f, right? So we have seen this as a transfer function is equal to h1 of f, or impulse response equal to h1 of t, right? So if the output is s1 of t, if the output is s1 of t, right? How to find its output? How to find this? That is the next question, right? Now what we are doing is, the FM signal is passed through the slope circuit, and we are getting s1 of t. This s1 of t is what we are supposed to pass to an envelope detector, right? So how to tackle this part, right? So the problem issue here is, this s of t is a band pass signal, right? S of t is a band pass signal, and this H1 of f is in turn as actually what a bandpass transfer function. You can see, right? It's a bandpass transfer function, and similarly, S of t is also a bandpass signal. If you remember the S of f, right? It had frequency contents from fc minus bt by 2 to fc plus bt by 2, right? So whenever we encounter actually what such bandpass signals, we have an easier approach, right? We have an easier approach instead of actually what finding the convolution or finding the response in bandpass domain itself. We can uh, come up with low pass equivalent. So when we did the derivation time, when we derived the time domain expression of wideband FM, right? We have studied something like this S tilde of t, right? S tilde of t, we told it is actually what low pass equivalent of band pass signal, right? So S of t is a band pass signal. S of t is a bandpass signal. Its low pass equivalent is S tilde of t. Right. So in one video where I discussed about Hilbert transform and all, I've discussed about this low pass equivalent. But if you have to move further from here, right, we should know the basics of low pass equivalent of a band pass signal and low pass equivalent of band pass signals and systems, right? So we should have a basic idea of this, right? So for that, we will right just see a simple example initially, right? So I'll consider a signal, right? Say I'll consider x of t, right? It is AC cos, sorry, 2 pi FCT plus say phi, right? AC cos 2 pi FCT plus phi, right? So how to, this is a uh, like uh, you can see it has a frequency content FC, right? Or else I'll write okay, fine, right? It has, it's a band pass signal. It's a band pass signal. Why? Because it doesn't have any low frequency content. Only frequency content present is FC. So how to convert it into the low pass equivalent? That is the question. So this low pass, how to convert this into low pass equivalent, right? For that, right? So we'll normally represent this x tilde of t. So how to convert this? That is the question, right? So we know by Euler's relation, this can be written as real part of AC into e power j 2 pi fct plus phi. Right? We can write it like this. So further, like it's just Euler's relation. E power j theta is actually what, cos theta plus j sin theta. E power j theta is cos theta plus j sin theta. So AC cos 2 pi fct plus phi I can write as real part of AC e power j 2 pi fct plus phi. I think you'll be able to, right, accept it. Right. Then further I can rewrite it as real part of AC into, I can e power j times a plus b is like e power j times e power jb. So it is e power j 2 pi fct times e power j phi, e power j phi, right? So I can write like this. Now if I have to get this low pass equivalent x tilde of t, what I should do is I should, right, if I suppress this real part thing, and if I suppress this e power j 2 pi fct, whatever is remaining, right, whatever is remaining, right, so that will be the low pass equivalent of this band pass signal. So this I can write x tilde of t now will be AC e power j phi, right? So what we have done, we have represented the signal as real part of AC times complex exponential, right? And in that, if you multiply it with e power minus j 2 pi fct, or if you suppress the e power j 2 pi fct part and the real part, right? So in detail, right, about this you will study in 6M, right? Even I have told, but here this is something similar to the phasor, right? So normally, when you were solving RLC circuits and all, right, one option is either you might have used Laplace transform, right? Other option is solving it in phasor domain actually what suppresses the time factor, and it will ease out your calculation, right? So this is actually what analogous to what phasor. So what we have done is how to convert, if I call it real instantaneous form or the band pass form, right? To convert that into low pass form, what I should do is I should represent it initially as real part of AC times complex exponential. So for this, we'll use actually what the Euler's relation, e power j theta cos theta plus j sin theta. If it is cosine of something, I can write it as actually what real part of that. And if it is sine, it's actually what imaginary part of e power j theta, right? So then if we suppress this real part and this e power j 2 pi fct, whatever is remaining, that is the low pass equivalent. That is the low pass equivalent. That is the idea, right? So and now we consider this s of t, right? Our s of t is, we will find out what is the low pass equivalent of s of t, and we'll stop here for the time being, right? So what is low pass equivalent of s of t? S of t is AC cos 2 pi fct plus 2 pi kf into integral 0 to t m of tau d tau, right? So this is our s of t, right? Now what we should do is we have to write it as, right? You don't have to write this step, you can straight away write it if possible, right? So if you simply suppress this 2 pi fct and cos, and if you write it as e power j the second term, you will get, but maybe we'll follow this step. So I can write it as it is equal to real part of AC e power j 2 pi fct into e power j 2 pi kf into integral 0 to t m of tau d tau, right? So I can write it like this. Now what I should do is I should suppress this and this, and whatever is remaining, that will be my low pass equivalent. So I can write s tilde of t, it is equal to AC e power j 2 pi kf into integral 0 to t m of tau d tau. This is the low pass equivalent of the band pass FM modulated signal, right? This is the low pass equivalent of band pass FM modulated signal. And similarly, if the low pass equivalent of this H1 of F, sorry, if the low pass equivalent of H1 of F, this is represented as H1 tilde of F, right? So now suppose we are able to find out the low pass equivalent of the signal S of t, that is S tilde of t, and similarly the low pass equivalent of the band pass response is H1 tilde of F, right? So then we can we have a relation. So I want you people to accept this, right? So this S1 of F, right? S1 of F is actually what the response when you pass this s of t through the slope circuit, whatever you are getting outside, that is s1 of t, its frequency response is s1 of f, right? So these things are band pass. The issue is these things are band pass. So what we'll do is we'll initially convert these things into low pass equivalent. S of t will be converted to low pass equivalent, and h1 of f will be converted to low pass equivalent, and the resultant we'll get actually what in terms of low pass equivalent. Then we can, right, frequency translated, we can get back the band pass equivalent later. It makes computation easier, right? It is actually what some analogous to how we are using phasor for solving RLC circuits, right? So this we can write S1 tilde of f, that is low pass equivalent of slope circuit output put for S of t as input, right? S of t as input, right? This S1 tilde of t, it will be equal to half times, you can write S tilde of f times h tilde of f, right? So where this S tilde of f is nothing but what? Fourier transform of S tilde of t, right? S tilde of f is nothing but Fourier transform of S tilde of t, right? So this result is what we'll be using. So maybe right. Uh, so so far what we have discussed is, right. So we have a indirect method. We have frequency discriminator. Frequency discriminator. Maybe I'll just quickly have a recap. Right. So direct method means it has a frequency discriminator. Frequency discriminator in turn has a slope circuit plus envelope detector. This slope circuit has a transfer function h1 of f, right? It is purely imaginary and linear function of frequency. Linear function of frequency. So we found what is this we found, right? So we found this to be equal to j 2 pi a times f minus fc plus bt by 2, right? For one range, and j 2 pi a times f plus fc minus bt by 2 for negative frequencies, right? And 0 elsewhere. We found this, right? So you know how these came, right? Then after that, what we are going to do is we are going to find the low pass equivalent of this h1 tilde of f, right? Then we will take our s of t, right? We will take our s of t, we will find its low pass equivalent, right? We will find its low pass equivalent s tilde of t, right? So then, right, if we use these two, right, the low pass equivalent, the resultant would be actually what? Half. If there is a half here, right, please don't miss that, right? When you are transforming uh, from band pass domain to what? Low pass domain, right? And in low like actual time domain, if it was convolution, frequency domain, it was convolution, there was no half, right? But here we do have an extra half, right? Half of h1 tilde of f times s tilde of f. This is equal to what? S1 tilde of f. This is what we have seen today. So in next class, right, the remaining thing we'll explore, right? So this was these concepts you may not have encountered so far. That's why I took some time, right? And if you are able to what break down the concepts into small chunks and actually what study like this, even if it is right a little bit complicated part, right? If you are able to relate it with the exact prerequisite what it is required, you can right learn it easily, right? So even now I admit that some of you might have felt it difficult, right? But not a problem, right? I'll just make this recording available. I request everyone to right watch that. And before I wind up, if I may ask someone to show the lecture notes you have taken, right? Whom should I call? Right? Is there any volunteer? No, maybe. Okay, Sahana. Right? Did you take down notes?
Yes, sir.
Yes.
But the last part I couldn't hear.
Last part.
I was not able to take the last part right beginning.
Okay, last which part you missed?
Um, yeah, from here. Yes, sir.
From
From
here,
here I missed.
right?
Yeah.
So, are you able to follow this? That's my question, right? If you are not able to follow, I admit it's I take it as my mistake, right? I should have explained it in a different way, right? So please feel free to tell whether you understood something,
Yeah, somewhat I understood, sir.
somewhat you understood, right? So if you have some doubt, like maybe in some muddiest moment which is not so clear, which would be that part? Can you tell me that, so that which part you have some doubt?
Once I need to go through, sir.
Once you have to go through, right? So okay,
Correct.
yeah, okay, yeah. Thank you, sir. Like, right, maybe I'll ask someone else. Right. So now, yeah, maybe I should ask Samartha. Samartha, are you there? Are you able to hear me? You are muted, I think. Or I can't hear you.
Hello,
Yeah,
sir.
yeah. Now I can hear you, Samartha. Yeah. So whether this part is clear, little bit,
Yes, sir.
right? So now,
If I,
if I ask you to watch, so anyhow, this topic is there in textbook. If I give it as a self-study topic, right?
yes, sir.
Will you be able to learn it? Maybe can someone come forward and like give a this seminar on this topic next class?
Self study will be little bit difficult.
Self-study will be a little bit difficult, right?
Yes,
So okay, in case if you have any doubt, will you be asking?
yes, sir. We'll ask about.
Right. Yeah. So maybe what I request is, right, all of you can. I'll share maybe in Canvas only. I only these two sheets, these like this particular topic. I'll share, right, your textbook part. Right. I want everyone to try it out. Right. And then next class we'll discuss. Right. What is that you understood? What you didn't understand? Right. So there are still more actually what aspects to be discussed. Right. But as this particular topic has many prerequisites, I've taken this and I'm trying to so break it into what small chunks and trying to discuss. Right, it would be more effective if you can ask some doubts if you didn't understand. Right, maybe I can explain it in some different way. Right, so if anyone has any doubt, please feel free to ask. Right, okay, then yeah, if any doubt is there, you can ask. Otherwise, right, you can leave now. I'm not asking anyone to switch on the video and show the um, lecture notes which you have taken down. Right? Maybe next week we'll have a quiz. Next class we'll have a quiz at the end. Right, about this. We'll have a quiz at the end. Yeah. So thank you so much for joining. Right. Those who have doubt can stay back. Right. Otherwise you can leave.